The paper title is A GCC-based compliance checker for single translation units identifier-related MISRA C rules. This is a joint work by Guanren Wang and Pongshen Chen at Zhongzheng University. Introduction. The recent rapid development of computer hardware and software brings ever more computing systems. For example, smartphones and smart home devices into our daily life. Some of them, for example, self-driving vehicles and robots, require high reliability to maintain their normal operations, and the failure can lead to serious problems or even endanger lives. Therefore, enhancing the reliability of software systems is a safety-critical issue. MISRA C was developed by the Motor Industrial Software Reliability Association. MISRA C is a well-defined software specification for the C programming language. Following this set of guidelines is expected to reduce the frequency of program mistakes. MISRA C was first published in 1998. MISRA C has been adopted and used across a wide variety of industrial and applications, including the rail, aerospace, military, and medical sectors. Here we focus on MISRA C 2012. The guidelines in MISRA C are classified as being either rules or directives. To check compliance with a directive requires additional information, for example, design documents or specifications, while compliance with rules can be assessed by analyzing solely the source code. There are 143 rules in MISRA C 2012, and these rules are further classified as mandatory, required, and advisory. Consider the scope of analysis. If rule violations can be detected in a single translation unit, the rules are labeled as single translation unit. Otherwise, the rules are labeled as systems, for which the whole program needs to be analyzed to detect violations. There are 40 system rules and 103 single translation unit rules. GNU Compiler Collection, GCC. GCC is an open source and popular compiler. GCC generates stable and high-quality code, and is almost a de facto standard compiler for Linux and open source communities. If GCC has the capability of detecting compliance with MISRA C rules, users can easily avoid writing unreadable programs. Target. In this paper, we modify GCC version 7.3.0 to support compliance checking of MISRA C rules. Focus on identifier-related single translation unit rules. They are rules 5.2, 5.3, 5.4, and 5.5, and rule 8.1 and 8.2. Our modification has one requirement. We want to make sure not to change the compilation result of the original GCC. The slide shows the internal structure of GCC Compiler Infrastructure. A C source code first enters the front end of the C language parser and is converted into an intermediate representation, generic. Next, entering the simplified stage. In this stage, the generic form be simplified to simple form. After several target-independent analysis and optimizations, simple form is lowered to RTL. Finally, the target code is generated from RTL. In GCC's front end, a tree structure is used to store program information. The tree structure is like this. GCC Compiler Infrastructure. There are two important built-in functions that are commonly used during tracing and verifying GCC front-end. Debug tree function. Much information is obtainable from tree structures. However, it is not easy to fully understand the tree structure. This function can dump tree information. The function inform. This function can output the program location and a suitable message. It needs two parameters, location T and the required message to be output. This function can be used to output warning message with location information. Strategy. There are a few documents describing GCC's internal design, especially the front-end part. In order to identify the proper program points in GCC to check the rules, we use the following steps to help the implementation. We create a test program that makes GCC issue the diagnostic messages of interest. The tested program needs not only to trigger warning error messages, but also to have characteristics following the rules we want to check. Then we trace the source code to understand the execution flow when issuing the messages. Finally, we design the checking algorithm and implement it. Here is an example. If we want to understand where GCC checks redefined macro, we can create a test program like this one and feed it into GCC. GCC will generate such warning message, and we can use the utility grep and the functions printf, debug tree, inform to clarify how GCC handles the macro redeclarations. This slide shows the variable declaration related and the single translation unit labeled rules. Rule 5.2 say that identifiers declared in the same scope and the namespace should be distinct. Rule 5.4 says macro identifiers should be distinct. The definition of distinct depends on the specification of C language. For example, in C90, the minimum requirement is that the first 31 characters are significant. And in C99, that is the first 63 characters are significant. Rule 5.5. Identifiers should be distinct from macro names. Rule 5.3 says that an identifier declared in an inner scope should not hide an identifier declared in an outer scope. This slide shows the examples. These two identifiers are the same in the first 31 characters, so they are not compliant. And these two identifiers are different in the first 31 characters, so they are compliant. GCC can detect macro redefinition and identifier redefinition, but GCC does not limit the length of characters. Even use the option -ANSI or -STD is equal to C90. In GCC source code, the function cpp creates definition calls one of redefinition to check macro redefinition. If error exists, call cpp add warning with line to show warning message. And the cpp create definition is located in libcpp macro.c. Identifier redeclaration is handled in the file c-decl.c. The function pushDecl calls duplicate decls to check identifier declaration, then call diagnose mismatched decls to issue warning message. This slide shows the code fragments to check macro redefinitions. And this is the function cpp create definitions. And it will call one of redefinition to check macro redefinition. If the error exists, and it will call cpp pad warning with line to show the error message. This slide summarizes the relationship between GCC current status and the identifier related rules. For rules 5.2 and 5.4, GCC can detect macro redefinition and identifier redefinition, but GCC does not limit the length of characters, even use the option -ANSI or -STD is equal to C90. For the rule 5.5, GCC cannot detect whether an identifier and the macro name are distinct. For the rule 5.3, the GCC option -w shadow can detect this issue. Implementation. In order not to interfere with compilation run by the original GCC, we use an additional data structure, a hash table, to record information for macros and identifiers. Then we can use this data structure to check identifier redefinitions and also consider significant characters. For example, in C90, it is 31 characters. We also record a variable scope information for checking rule 5.3. Even it can be detected by the option -w shadow. The C_scope structure, and it contains a variable current scope. It records depth information, and this information can be used to check the rule 5.3. Implement and insert the codes for checking rule 5.2, 5.3, 5.4, and 5.5 into the functions cpp create definition and push decl. Because of the time, we only briefly introduce the part of rule 5.2 to 5.5. The other part, please check our paper for the detailed information. Experiment. The evaluation environment is Ubuntu 16.04 run on an Intel Core i7 PC with 8 GB RAM, and the modified GCC version is 7.3.0. The tested benchmark are from two parts. The one is an example code from MISRA C 2012 specification. The other are from example suite. It is obtained from this website. And this is a snapshot of example suite website. For the tested benchmark program, our modification can correctly assess compliance with the target MISRA C rules. Conclusion. The MISRA C specification provides rules for programmers that reduce the likelihood of code being incorrectly written or behaving in unintended ways. MISRA C has been adopted and used across a wide variety of industries and applications, including the rail, aerospace, military, and medical sectors. In this paper, we implement MISRA C compliance checker based on GCC Compiler Infrastructure. We focus on single translation unit labeled identifier-related rules. For the tested benchmark programs, the modified GCC compiler can correctly assess compliance with the target MISRA C rules. We proposed an approach to figure out where to intercept the compliance compilation flow and insert the checking code. Pick up a proper diagnostic message similar to the target MISRA C rule. Use grep and printf to find and ensure where to insert the checking code. Use debug tree and built-in macros, for example, tree type, tree operand, to study the tree structure. Use debug tree and inform to realize the program behavior. Future works. We will continue to enhance GCC for supporting more MISRA C rules. And we will evaluate whether the detector can be implemented as a GCC plugin. And the benefit is it is easy to integrate with different GCC versions. And GCC 10 version 10 provides a static analysis path that can diagnose various kinds of problems in C codes at compile time. Such static analysis path is useful to detect system-labeled rules. And we want to evaluate whether the static analysis path is useful for single translation unit labeled rules. Thank you for listening.